Well, welcome back. This is not a mission that's impossible for us today. We have implicit differentiation one last time, and we're going to focus on some more AP-type problems. So, take good notes, and hope you enjoy. Before we dive into that AP problem, let's get one example under our belt. Now, we've said over and over, read these functions out loud before you even attack their derivatives. This side says x times sine y, and I'm just going to rewrite that for myself. It's the quantity x times the sine of y. Okay, and I said times, so I know I've got a product rule in there. Equals 3y, now remember that's not product rule because 3 is just a coefficient, plus the cosine of 2x. So the slower you read it to yourself, the more obvious the problem should become. Alright, so why don't you pause it at that point, just take the first line of your derivative and see if ours match. So hopefully you were honest, you paused it, and you got the same thing. So I have my first term, the derivative of sine y is the cosine of y, but because there's a y, I need that dy dx. Plus the second term, sine of y times 1. Equals the derivative of 3y is 3, but again, because there's that y, I need dy dx. Cosine becomes negative sine, keep the inside, derivative of the inside. At that point, if you're feeling good, I'm just moving the dy dx's on one side and moving everybody else to the other. And, after that calculus step, I'm assuming you can get to this answer pretty quickly on your own. I moved my dy dx's over, I factored it out, and divided by that term. And there you have it. Alright, I think we're ready to build up to that last AP problem. Example, consider the curve in the xy plane. So very nicely they gave us this function. And A, is it possible for this curve to have horizontal tangent lines at points where it intersects the x-axis? Then find all the points that satisfy these conditions or explain why they do not exist. Alright, so to me, there was two key math things I had to get out of this. The first one, of course, is horizontal tangent lines. Okay, we talked about that last week. So I'm going to abbreviate that as HTL, horizontal tangent lines. And we said if you ever forget, just draw yourself a horizontal tangent line, and the whole course is about slope so far. So what do you know about the slope of this? Well, it has a slope of 0. And in slope, calculus means take the derivative and set it equal to 0. So that's the first thing I need to do. The second thing you had to catch is they were very specific where this had to happen. It said where it intersects the x-axis. Okay, picture your graph. Picture every time it intersects the x-axis. What is special about every single one of those points? I might call this negative c, 0, negative a, 0, positive c, 0. Notice everybody who intersects the x-axis has a y value of 0, and that is the key there. And you don't have to memorize anything. If you forget what intersects the x-axis means, draw it out and ask yourself what's true. So now that we realize we have to do two things, I'm going to start with the calculus part. I'm going to take this guy's derivative and set it equal to 0. So pause it, take the derivative, and see if it matches with mine. So hopefully your derivative matches. Remember, you could be equivalent if you had this value as a negative, a positive, a negative, and a positive. So keep that in mind. Now, we said horizontal tangent line meant take that derivative and set it equal to 0. So now we'll just put an equal 0. Now again, you don't have to memorize anything. Think, if a fraction equals 0, which part was actually 0? Well, that's 0 divided by any number. So I'm really just setting my numerator equal to 0. So 2xy minus 3x squared equals 0. Now, all your gut hopefully really tells you at this point is probably just to factor and pull out a GCF. I'm going to pull out that x, and I get 2y minus 3x equals 0. Tee it up. I get x equals 0, and x equals, let's see if I subtract that and divide that, 2y over 3. Now, if you recall, and I'll scroll back up there, the question said, is it possible for this curve to have horizontal tangents where it intersects the x-axis? Now remember, that meant the y value is 0. And then find all the points that satisfy this condition. So I got two solutions at the moment. First of all, I got x equals 0, but remember, we already know the y value has to be 0. So now I have to test that and see if it's true. And I'm just going to substitute those two into the original. So recall I had x cubed plus y squared minus x squared y equals 9. And when I take those and substitute them in, basically I'm getting, remember, x is 0 and y is 0. 0 plus 0 minus 0 equals 9. Does that make any sense? Does 0 equal 9? Well, of course not. So all I'm saying is this is not a possible point to have a horizontal tangent line where it intersects the x-axis. Now, remember, I did get something here, so I also have to test this value. But keep in mind, we already know that y is 0. So if y is 0 in this case, and I have 2/3 y, that implies that x has to be 0. Well, that's the same point we just tested, so we know that's not true either. So in this case, I can say there are no points where we have a horizontal tangent line at the x-axis. Now moving on to part B, it's an extremely similar problem. You'll notice we just changed one thing. So this is the same function from my previous example. Is it possible for the curve to have horizontal tangents? Okay, so there's my first horizontal tangent I need to pull out, where it intersects the y-axis. Okay, so the last one was horizontal tangents at the x-axis, and remember, again, I'm not memorizing, that just meant set your derivative or your slope equal to 0. Now the y-axis, sketch it out, okay? What's special about every point a function crosses the y-axis? What value do you know? Well, certainly, I know the x value is 0, it's the y value that moves. So I can say x equals 0. Now half my work is done for me because in part A I already figured out my derivative and set it equal to 0. And again, after I set that fraction equal to 0, the only part I'm really setting equal to 0 is the numerator because 0 divided by any number is 0. So I'm just going to steal that piece I had from above and say x times the quantity 3x minus 2y equals 0. And that's fair game on your test or your exam. If it's already in part A, you can just rewrite it. So when I tee it up, I get my x equals 0. And I get x equals, let's see, that was 2y over 3, or 2/3 y. Now, remember, all I know at this moment is the x value is 0. Okay, so if I let x equal 0, I need to plug it back in that original equation, which was x cubed plus y squared minus x squared y equals 9, and see if I get a y value or just some garbage that doesn't exist. So if I plug in my 0, that kills that term, and I get y squared equals 9. Now, the easiest thing to forget, and somebody does it every year, when you take that square root, you are physically putting that square root in. You have to remember that you actually get plus and minus 3. So right from that point, we actually get two solutions. We get 0 positive 3 and 0 negative 3. Now we could have even more solutions because we have this term over here, so let's think about this. All we know is that the x value has to be 0. So I get 0 equals 2/3 y, and of course that only happens when y equals 0. Now we tested this in the last problem, but I'll show you again real quickly. If I took that equation x squared plus y squared minus x squared y equals 9 and plugged in that 0, 0, I get 0 equals 9, which doesn't make any sense. So we kill this side. So I can say, yes, let me just revisit that question. Find all points that satisfy this condition. So yes, I have 2 points where there is a horizontal tangent line where it intersects the x-axis. We have 2 points where there's a horizontal tangent line where it intersects the x-axis. Well, believe it or not, that does it for us tonight. We'll look forward to one more day of practicing implicit differentiation, and have a great night. We'll see you tomorrow.